Okay, today we're going to do the final exam review, and I've picked out 23 problems similar to the 23 on the final. Starting with number 2, solved by the square root property. The quantity 2 minus 3x squared equals 8. Does take us way back to the beginning of the semester when we were doing chapter 1. And to get rid of a square, every property or every operation has an opposite. The opposite of squaring something is a square root. So if we square root on both sides of the equation, and whenever you take a square root of a plain old number, it'll be plus or minus that value. So we get plus or minus square root of 8 on the right side. The good thing is the square root of a square cancels out, and the left side is just 2 minus 3x. The square root of 8 can be simplified down. There's a pair of 2's in it with a 2 left over, so you'd get plus or minus 2 square root of 2 for that in its most simple form. Now the goal is just to get x by itself. So we subtract 2 from each side, and you just, that negative 2 plus or minus 2 square root of 2, literally you just write that. Negative 2 plus or minus 2 square root of 2. Divide both sides by negative 3. Now there's a little tricky part to the end here. The negative 2 divided by the negative 3, in the front of the fraction, two negatives can make a positive. So they can switch to 2 and 3. Notice that the 2 square root of 2, it was plus or minus before, and it still says plus or minus now. And that's basically, you could technically think of it, it switches to minus or plus. We just never write that. Plus or minus and minus or plus, they're the same thing. So you're really doing both anyway. A positive divided by a negative is negative. A negative divided by a negative is positive. You're still getting a plus or a minus. So really it kind of seems like only the front negatives are canceling each other out, but really all three of them are. So the first answer is 2 plus or minus 2 square root of 2 all over 3. And some of these problems on the review, the endings to these, the algebra behind all this, is actually a little more difficult on the review than it is actually on the final itself, so you should find that you're not even going to see something weird like that on the final. But all we have is these problems they created here to work with. 3, solve by the quadratic formula. Now you can simplify this a little first before you get started. We need to see it in quadratic equation form. And that's where you have the ax squared first, then the bx, and then a number equal to 0. So that's what we got to do first, is distribute the negative x into this quantity and get negative 3x squared minus 2x equals 5. This is doing negative x times each of those in the parentheses. Then we want to get it equal to 0, and even though you could just move the 5 over more quickly, I like to have as many positive terms as possible. So I would rather add the 3x squared and add the 2x over to the right side. It doesn't matter which side's 0, we just need one side to be 0. The advantage of that is everything's positive now. It makes doing the quadratic formula a little easier. It'll still work if you move the 5 and have everything negative, but it's just more chance of errors when you're working with negatives. So this way we get to have a equal 3, b equal 2, and c equals 5. So going to the quadratic formula, it's the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. So the opposite of 2 is negative 2, plus or minus square root, 2 squared minus 4, that minus 4 is always part of the formula, times the a3 and times the c5 all over 2 times 3. So first thing you want to do is get that inside of the radical down to a single number. 2 squared is 4. 4 times 3 is 12, times 5 is 60. So we get 4 minus 60 and we get a negative 56 inside the radical. You can also do the denominator. 2 times 3 is 6. Negative 2 plus and minus the square root of negative 56 all over 6. Square root of 56 can be simplified. It's got a 14 times a 4, and the 4 can be 2 times 2, but the 14's left over. So that can simplify to 2 square root of 14. And with the negative in the radical, that brings out the imaginary number I. So it's really 2 square root of 14i, although with i's we like to put them in front of radicals so we don't get them confused. Is the I in or out of the radical? By putting it in front, there's no doubt it's not in the radical. So that's the reason for 2i square root of 14. Now, whenever you get to this situation, sometimes people think they're done at this point, and sometimes you actually are. But look at all the front numbers. There's a -2, there's a positive 2, a plus or a minus 2 in front of the I, and then there's a 6 in the denominator. All three of those can divide by 2. And if you're able to divide all three of them, then you would want to. So divide them all by 2. -2 divided by 2 is -1. 2 divided by 2 is 1, and 6 divided by 2 is 3. Or you can even split it into 2 fractions and do the -6 divided by 2 and get -1/3, reducing that down by 2, plus or minus. The 2 over 6 can become 1/3. Now notice here we put the I in the back, because if we put it after the fraction, then clearly it's not inside the radical. But it wouldn't be wrong to put it in front of it either. And then you don't reduce the square root of 14. You can't reduce a number that's in a radical with a number that's not, so it's just the front numbers. 2 and 6 reduces to 1 and 3 in both fractions, basically. So that was number 3. The third problem is like 6c. 6c has solving each equation. There's a square root of x plus 2, and then outside of the radical there's a minus x equals 2. So you're going to want to get the radical as isolated as possible. We want one side of the equation to have the radical and everything else on the other side. So I would add the -x over to the other side first. That gets the radical all by itself. Square root of x plus 2 equals x plus 2. To get rid of a radical, it's the opposite of that other problem we did. We use a square. Squares and square roots cancel each other out. But you do have to square both sides of the equation. The left side's easy. The square cancels the square root, so you just have x plus 2. The right side, you're going to want to write that twice and FOIL it out. X plus 2 times x plus 2. You don't just square the x and the 2. You end up getting x squared plus 4x plus 4. Because we have a quadratic equation at this point, we want to get one side equal to 0. It's best in all quadratic equations get one side equal to 0. Then you may be able to solve it with factoring, completing the square, or quadratic formula. So I'm minusing x and minusing 2 to make the left side 0. 4x minus 1x is 3x. 4 minus 2 is 2. So we're left with 0 equals x squared plus 3x plus 2. Yes, the quadratic formula would work, but if you can factor it, it's a lot less work. And here, x plus 2 times x plus 1 is what makes x squared plus 3x plus 2. We needed two numbers that multiply to 2 and add up to 3. Then, because you have a product equal to 0, then you can set each part equal to 0. So either x plus 2 equals 0 or x plus 1 equals 0. Leading to two answers, x equals -2 or x equals -1. Okay, so that was a square root equation. Now in number 8a, now we're solving an inequality, and it's even a quadratic inequality. It's got an x squared in it. X squared plus 3x minus 4 is less than or equal to 0. So this one kind of starts off the way the last problem just ended. There is a way to factor x squared plus 3x minus 4. Two numbers that multiply to -4 add up to 3 would be +4 and -1. So you get x plus 4 times x minus 1. Now, even though I could think of this as if it was equals 0, I would just say the answers are -4 and +1. With an inequality, you don't get to say, okay, just put less than or equal to on both of these. It doesn't work that way. But think of what would make them equal 0 first. -4 and +1 makes this equal 0. Then you take those two answers, or however many there are, and I put them on a number line. -4 is on the left, +1's on the right. because the original inequality has an or equal to, then we put closed circles on them. And then basically what it comes down to is we're going to create three sections of this graph. The left of -4, in between -4 and 1, and the right of 1. You just use 3 test points. Pick any number less than -4. I choose the most convenient number. The first number, whole number less than -4 is -5. Pick any number between -4 and 1. Why not pick 0? That's a nice number to work with. I always pick 0 whenever I can. And then anything bigger than 1, so why not use 2? So we want to check each of the 3 regions. Each of the 3 regions may or may not be in the solution. So I'm going to check -5, 0, and 2 by plugging them into this factored statement. You could plug them into the original, but it's a little quicker if you plug them into this factored one, the second line. Stick in -5 where both of those x's are. -5 plus 4 and -5 minus 1. That's what I'm doing down here. -5 plus 4 times -5 minus 1. Sticking in -5 for both x's. Well, by order of operations, you do the parentheses first. -5 plus 4 is -1. -5 minus 1 is -6. So then -1 times -6 is clearly 6, but we don't really care that the answer is 6. All we care about is the answer positive or negative? A negative times a negative is positive. So what this is telling us is any number we plug in less than -4 is going to cause the product here to be positive. But we want less than or equal to 0. Less than or equal to 0 means we want negative numbers. So the left region's no good, and we're not going to use that in part of our solution. I checked it, and we didn't get a negative there. Do the same thing with 0 and 2. Plug in 0, plug in 2, just do the calculations. The second one turns out to be 4 times -1. That is negative. That's what we were looking for, negatives. The third one is 6 times 1. That's positive. We don't want that. So out of the 3 sections, it turns out only the middle section is good for us. And the way you write the answer then, they have this thing called interval notation. So we want all the numbers between -4 and +1, including both of them because of the or equal to. So we write a bracket for the -4, a bracket for the 1, and by putting a comma between it, it a little bit looks like a coordinate, but this doesn't mean x is -4 and y is 1. This means that we want all real numbers between -4 and +1. Just like the graph shows. Okay, the next problem is like 10b. Now we're doing an absolute value inequality. Absolute value of 7x plus 8 minus 6 is greater than -3. Just like that radical equation, if you have these special equations and there's stuff inside your grouping symbol and stuff outside of it, get the outside stuff out of here first. I would add 6 first just to get that out of the way. Add 6 to both sides. This isolates the absolute value all on one side, so there's nothing outside of the absolute value. And then it turns out it's greater than 3 because -3 plus 6 is 3. Now these problems are usually tricky for people the first time they see them. There's one inequality you can write that's exactly like it looks right here. Just take the bars away. 7x plus 8 is greater than 3 is what it looks like. So we do that first. 7x plus 8 is greater than 3. But we can do a second one where we say 7x plus 8 is less than -3. So you switch the greater than to less than, and you switch the outside 3 to -3. Don't switch the inside stuff. This is 7x plus 8 on both halves. Some people put 7x plus 8 for one of them and 7x minus 8 for the other. You don't switch that. Only the 3 switches to 3 and -3, and then one's greater than, one's less than. And if the original problem is greater, you get an or statement. If the original one is less than, then you get an and. And it makes a difference if you have or and. And I remember that because greater, sounds like or. Greater, some people even say it fast and say great or. Great or, that's an or problem. Less than sounds like and. Now you're just solving this. Minus 8 to both sides. Divide by 7. And again, some of these review numbers come out weird, but it's x is greater than negative 5 over 7. It doesn't reduce, so we just leave it like that. Minus 8 on this one gives you a negative 11. Divide by 7, and again it doesn't divide. So we got two statements here. X is greater than negative 5 over 7, or x is less than negative 11 over 7. This could actually be the answer. If they wanted an inequality version of the answer, you could leave that. But since the directions want interval notation, it might be helpful to draw a graph of this. Negative 11 over 7 is smaller than negative 5 over 7. The bigger it looks on the negative side, the smaller it actually is. So I made a number line with the smaller number on the left, negative 11 over 7, the bigger number on the right. Notice that they're greater than and less than's without the or equal to, so then I put open circles. And if you're going less than negative 11 over 7, less than's to the left. If you're doing greater than negative 5 over 7, that's to the right. So this is kind of like that last problem, except now instead of the middle region being the answer, we're getting the two outside regions. So the interval notation for this is you start way out at negative infinity. You want to travel left or right. You come across till you get to this first open circle, negative 11 over 7. And then you just write negative infinity, comma, negative 11 over 7. That's a way to say I'm between those two. And then because it's an open circle, we put a parenthesis instead of a bracket. Infinities are always parentheses because you can never get to infinity actually. For an or, we put the little u for the, that's a set notation. The little horseshoe U shape means or, and if it's upside down it means and. So this is the way to write or when there's a separate second section of your graph. Now we're going from negative 5 over 7 all the way to infinity. So again, parenthesis, negative 5 over 7, comma, infinity, parenthesis. So here's the answer to 10b. Number 11, they have a part A and a part B. Part A wants the length, to find the length of the line segment, which is really distance formula. Part B wants the midpoint. And all the problems they have in this textbook, they always put both of these together. So I couldn't get a problem that just did distance formula. So we'll just go ahead and do both. So here are the two original points, P and Q. It may be helpful to label them x1, y1, and x2, y2. So that means the first x, the first y, the second x, and the second y. The distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. So we're going to grab the second x, negative 5, minus the first x, 3. Negative 5 minus 3. Then it gets squared plus the second y minus the first y. The second y is negative 2. But the first y is negative 4. So you're literally doing negative 2 minus a negative 4. A double negative like that switches to plus. Negative 2 plus 4. So notice on the x's it's not a double negative. It doesn't switch to plus. The y's are a double negative. Then we switch to plus. As always, do the parentheses first. Negative 5 minus 3 is negative 8. Negative 2 plus 4 is positive 2. Exponents would come second. Negative 8 squared is 64. 2 squared is 4. Anything squared is positive. 64 plus 4 is 68. And then we can factor this down and see if there's any pairs in it. We always want to simplify radicals if we can. 68 is 4 times 17, and 4 is 2 times 2. There are a pair of 2's in it. So the best way to write the answer is 2 square root of 17. For the midpoint formula, it's a little bit easier because it's literally like doing an average. You add up the two x's and divide by 2. You add up the two y's and divide by 2. And if you're doing 3 plus a negative 5, that's the same thing as 3 minus 5. Negative 4 plus a negative 2 is the same thing as negative 4 minus 2. 3 minus 5 is negative 2 in the numerator. Negative 4 minus 2 is negative 6. If you get odd numbers, you just leave them over 2. If this was negative 3 over 2, I would just leave it like that. If they're evens, you should divide them. Negative 2 divided by 2 actually equals negative 1. Negative 6 divided by 2 actually equals negative 3. So if they're even numerators, divide them by 2. If they're odd, you just leave them as fractions. Okay, next we want to do number 14. Here's the general form of a circle. They want us to transform it to the center radius form and then tell them what the center and the radius are. You can't tell the center and radius from this version, but if we do some manipulation to it, we can put it in a form where you can see the center and radius. And this involves completing the square that was taught way back in chapter 1, and then you're using it in some future chapters too. So I would group the x's together, do a parenthesis and an x squared plus 2x plus blank. Then group the y's together, parenthesis y squared minus 10y plus blank. Move the positive 10 to the other side of the equation, make it a negative 10. And then for each blank on the right, you'll have one on the left too. And I kind of do this backwards by doing the second step first. So I look at my x squared plus 2x, and then there's a plus blank right after that that I'm not showing you on purpose. And I don't, a lot of books will teach you to fill the blank in first and then go down to the next line. I like to go down to the next line first, because it always turns out it's half of that middle number. Half of positive 2 is positive 1. So you get x plus 1 quantity squared. Then the number 1 squared, if you square the 1, that's why it's called completing the square, 1 squared actually equals 1, so that's what goes in the blank. So I actually go down first from the positive 2 to the positive 1, square it, and come back up to the 1. And then when you put a plus 1 here on this left side of the equation, then way over on the right side we put another plus 1 to balance it out, next to that negative 10 that we moved over there. Same thing with the y's. There's a y squared minus 10y, so we do half of negative 10, which is negative 5. So that'll turn into y minus 5 squared. Negative 5 squared is positive 25, so that's what goes in the blank. And put a positive 25 over in this blank. So here it is a little further out where you can see everything at once. And then you add all these together. Negative 10 plus 1 plus 25 adds up to 16. This is the center radius form when you have x plus something squared plus y minus something squared equals something. When it's in this form, you can see the center and the radius. The center is the opposite of each number in parentheses. The opposite of positive 1 is negative 1. The opposite of negative 5 is positive 5. The radius is the square root of this equals number. Square root of 16 is 4. So there's a center of negative 1, 5 and a radius of 4, which is the answer to the problem. Now jump down to 22F. Now we want to write the equation of a line. Do this without graphing. We want to go through the coordinate 2, negative 1 and be parallel to 3x minus y equals 1. So we're given one line and we want to get another line that's parallel to this one and goes through a given point. So the first thing you would do is take the given line, 3x minus y equals 1, figure out what the slope of that line is. You can't tell in this version. You can't see the slope till the y is by itself. So I took the 3x minus y equals 1, I subtracted 3x from each side. Now when you do that, don't lose the negative on the y. The y is still negative. The 3x's cancel, but the y is still negative. The other side becomes negative 3x plus 1. But we need positive y before we can see the slope. So divide everything by negative 1. You get y equals positive 3x minus 1. And really all I care about is the positive 3. That's the slope. The given line has a slope of 3. Our line is parallel to it. Parallel lines have the same slope. So now we know our line has a slope of 3. So I just use y equals mx plus b. That'll get you the equation of any line. Plug the 3 in for the m now. And since we were given a coordinate way back at the beginning, our line has to go through this point. A coordinate is an x and a y. So you can plug the -1 in for y. And you can take the 2, which is the x, and plug that in for x into y equals mx plus b. So we're just temporarily plugging in for y and x, just so we can figure out what b is. B is the y-intercept. So 3 times 2 is 6. Subtract 6 from each side. B equals -7. So now we know the slope of our line is the same as the slope of the other line. It's 3. And we know the slope of our line is -7. While the other line had a... sorry, not a slope. The y-intercept is -7 of our line. The other line had a y-intercept of -1, but ours is parallel to it. It's not the same as it. They have the same slope, but they don't have the same y-intercept. So the final answer is y equals 3x minus 7. We plug in the 3 for the slope, and we plug in the -7 for the y-intercept. (23) just says graph the slope and the y, or give the slope and the y-intercept of a line, and then graph it. That's kind of how we started the last problem. Take this equation, it's not in the proper mx plus b form. We got to get y by itself first. Subtract x from each side. Notice the 3y will still be negative though. -3y equals -x plus 9. Divide everything by -3 to get the y by itself. The negative x over -3, that's the same thing as positive 1/3, because the two negatives will be a positive. Positive 9 divided by -3 will be -3. So the first half of the answer here is that the slope is positive 1/3, the y-intercept is -3. And it's important to know those two things, because then you can graph it like this problem wants. The other problem didn't want us to graph, but here we want to graph. To graph a line, you start at the y-intercept, the y-intercept. Go to the y-axis and get to -3 on the y-axis, which is 3 below the origin. Then from that exact spot down there at -3, now we want to use the slope to get another point. 1/3 means you go up 1 and 3 to the right. Up 1 to -2, 3 to the right, and then you just draw the line right through that. Okay, next we have 27C. They give us an f of x, x squared minus 3x minus 5. They give us a g of x, 2x plus 1. Part C wants us to do f of g of 2. So this is the kind where you do these one at a time, and you do the closer one first. We want to do g of 2 first. F, there's both given functions. F of g of 2 are the directions, but we do g of 2 first. Plug it, find g, don't worry about f right now, just g. 2x plus 1, right where the x is, plug in a 2. That's what g of 2 means. So instead of 2x plus 1, it's 2 times 2 plus 1. Multiply first, 4, and add second and get 5. So this first answer is not actually part of the answer. It just helps us to get to the second answer is the only answer that matters. The first answer just helps us to get to it. Since g of 2 equals 5, imagine sticking a 5 right here. Since g of 2 equals 5, then the 5 can replace it since they're equal to each other. And then you in essence have f of 5, since g of 2 is 5. So that's how I think of it, is I take my first answer and then I plug that in with the other letter, the letter that's in the front, f. Now I want to do f of 5. F had two different x's. There's an x squared and a 3x, so you got to put a 5 for both of those x's. So then we get 5 squared minus 3 times 5 minus 5. The last 5 was already there. But we're also putting 5s in for both x's. Now it's just order of operations. Exponents first, 25. Multiply second, 3 times 5. Notice we don't do 25 minus 3. Multiplying happens before subtracting. So it's 25 minus 15, which is 10. 10 minus 5 is 5. Number 30 says use transformations to sketch a graph of this, and it's a quadratic graph. If you know how y equals x squared looks, a u-shaped parabola, the question becomes what does the minus 5 and the plus 4 do to the graph? And this is how I always treat these. If you see a number with x in a grouping symbol like this, x minus 5, that minus 5 is in the grouping symbol with x, you do the opposite of what it looks like. Normally negative 5 on the x-axis is to the left, so instead we shift it to the right 5. When it's not in a grouping symbol, it's not with x, the plus 4 is separate, that's not with x, so that affects y, but the ones that affect y, you do them like they look. So plus 4 on the y-axis is normally up 4, so yep, it's up 4. So all we do is take a u-shaped parabola that goes through the origin normally, and we want to shift it to the right 5 and up 4. So I went to the right 5, up 4, put the vertex dot, and then just draw a u-shaped parabola going upward from there. Okay, 34, 35, and 36 kind of all go together. 34 says use the factor theorem and synthetic division to determine whether x plus 4 is a factor of this long polynomial. So there's a long polynomial given, fourth power, 5x to the fourth all the way down to 16. Is x plus 4 a factor of it? That's the same question as asking, is x equals negative 4 a 0 or not? And for these, you want to work with the 0, you don't want to work with the factor. They sometimes give you a 0, they sometimes give you a factor, but you always work with the 0. There's two ways to do this. One is to use synthetic division. With the 0 that's given, do the negative 4 in the house. Take the coefficients off each term, as long as no exponents are out of order or skipped. We've got a fourth power, third power, second power, first power, and a 0 power. So they're all in order, nothing skipped. We need 5, 16, negative 15, 8, and 16. So you write all those down. You start by bringing down the front number, bring down the 5. 5 times negative 4 is negative 20. You multiply up, and then you add straight down. 16 plus negative 20 is negative 4. Repeat the process till you go all the way across. Negative 4 times negative 4 is positive 16. Negative 15 plus 16 is 1. 1 times negative 4 is negative 4. 8 minus 4 is 4. 4 times negative 4 is negative 16. 16 minus 16 is 0. So if you get 0 for a remainder, the last answer is the remainder, if there is one. If it's 0, there's no remainder, and that's when you say, yes, this truly is a factor of it. X plus 4 is a factor of this function, this polynomial, and then negative 4 is truly a 0 of it also. The other option is just to figure out f of negative 4. If I just plugged in negative 4 to the original function, which might be a little easier in this case, especially with a calculator, if you plug in a possible 0 into a function, and the answer comes out exactly to 0, then yes, that is a 0 of it. Hence the name 0. So you really could have done this either way, either with synthetic division or just by finding f of negative 4. If it comes out to 0, yep, it's a 0. If it's anything but 0, then no, it's not a 0. Let me jump down to 36 next, because it's shorter and it'll fit on my paper better. Here we have a polynomial, and they want to know what's the end behavior of the graph, which is one of these 4 pictures here. Either both arrows are going up, both arrows are going down, or you got one of each, one up and one down. And it's all determined by the degree and the leading coefficient. So make sure you find the one, in case they're out of order, find the term with the highest exponent. 9x to the 6 is all that matters here. The 9 is a positive number and the 6 is an even degree. So we've got a positive leading coefficient 9 and we've got an even degree 6. Anytime you have a positive even, the end behavior is the one where they're both going up. So it rises on the left and rises on the right. And just to review all the cases, there's 4 possible cases. If you get a positive odd, then it acts like an x to the third and it'll fall on the left and rise on the right. And I just memorized these two. If I get a positive even, it looks like this. Positive odd looks like this. If you get a negative of either one, you just flip both arrows. So instead of having a positive even, if you get a negative even, instead of them both being up, they're both down. And if you get a negative odd, you do the opposite of the positive odd. Instead of going down first and up second, it reverses to up first and down second. So instead of having 4 things to memorize, if you just memorize the first 2 positive cases, then it's easy to get the 2 negative cases. Okay, now go back to 35, because this one's a little bit longer. Find all complex zeros of a long polynomial, given that 5 is a 0. So because it's 3x to the third, the degree is 3, there can be 3 zeros on this problem. One of them is given to us already. So there's 2 more that we might be able to find. And this is why we did this with number 34 also. Once you have your polynomial, if you know a 0 is 5, you can do synthetic division with that. And you should get a remainder of 0, because we know it's a 0. So I take the original polynomial, 3x to the third, negative 9x squared, negative 31x, and plus 5. Use the 0, 5 in synthetic division. Bring down the 3. 3 times 5 is 15. Negative 9 plus 15 is 6. 6 times 5 is 30. Negative 31 plus 30 is negative 1. Negative 1 times 5 better be negative 5, because 5 minus 5 is 0. Yep, the remainder is 0. So we knew that was going to happen, but the key thing is on the answer, 3, 6, and negative 1, by doing synthetic division with that known 0, we're dropping our degree from 3 down to 2 now. This will now be 3x squared plus 6x minus 1. And sometimes it comes down simple enough to be solved with factoring. This one turns out it doesn't factor, unfortunately. But then we can employ the quadratic formula as always, which is why we learned that in chapter 1. Quadratic formula will solve any quadratic. Factoring only works some of the time. It doesn't work every time. So the ones on the test come out nicer. You'll be able to factor them and get the answers quicker, but you can do this long quadratic formula process. It's good to know how to do this. Don't forget to get the whole radical down to a single number. And it comes out to 48 actually this time because of the double negative. 48 is 16 times 3, 16 is 4 times 4, so you can actually write 4 square root of 3 for that. Negative 6 plus and minus 4 square root of 3 over 6. So again, all 3 of these numbers that are not inside the radical, 6, 4, and 6, they can all divide by 2. So negative 6 divided by 2 is negative 3. 4 divided by 2 is 2, and 6 divided by 2 is 3. This is the answer they had. Negative 3 plus and minus 2 square root of 3 all over 3. That's actually 2 more zeros right there. Because you got the one with the plus and you got another one with the minus. It's actually 2 separate answers even though it looks like one answer. But again, if this problem, once you got to here, a lot of times you can just factor this after you do synthetic division. That's what's nice about it, is you usually get a simpler problem and it'll just factor real nicely. You get 2 separate answers right off the bat from there. This one unfortunately was a little more complicated, so we had to use quadratic formula to finish it. Okay, one other thing here in this third chapter was given rational functions, which is a fancy way of saying fractional. We've got a polynomial in a numerator and a polynomial in a denominator. Number 39a, f of x equals 2x plus 6 over x minus 4. we want to find vertical, horizontal, and oblique asymptotes. And the vertical asymptotes are coming from any zero in the denominator as long as the fraction is fully reduced. So if you have a way to factor the numerator, denominator, and cancel stuff, then you should do that first. But most fractions that are given to you already is factored as much as possible and reduced as much as possible. So there's no way to reduce this fraction at all. So what makes the denominator equal 0? The denominator is x minus 4, so what would make it 0 would be positive 4. That's the vertical asymptote. Any 0 from the denominator as long as it doesn't reduce first. So the vertical asymptote rule is easier to remember. It's just all the zeros from the denominator. There might be no zeros, there might be 1, there might be 2, might be 20. Just anytime the bottom equals 0, that can be a vertical asymptote as long as it doesn't reduce with the numerator. Horizontal asymptotes have 3 cases. If the numerator degree is bigger, if you have a degree that's higher in the top, you won't get a horizontal asymptote. It'll be none. If the bottom degree is bigger, then you automatically get y equals 0. But this is the third case, 2x plus 6 over x minus 4. Both of these parts of the fraction have a degree of 1. 2x to the first and x to the first. When the degrees equal each other, the horizontal asymptote is the ratio of the leading coefficients. The top leading coefficient is 2 here, the bottom leading coefficient is 1. So we literally get y equals 2 divided by 1, which is y equals 2. And if the denominator degree is bigger, you automatically get y equals 0 for a horizontal asymptote. If they're equal in degrees, then it's y equals the 2 leading coefficients divided. And if the numerator is bigger, then you don't get one. And oblique asymptotes are sideways asymptotes. They only happen in the case when there's no horizontal asymptote, this third case down here. So if you're able to get a horizontal asymptote answer, you won't get an oblique asymptote. And when you can't get a horizontal asymptote, like in case 3 here, you won't always get an oblique asymptote. It'll only happen if the top degree is 1 bigger than the bottom. So anytime the top degree is bigger than the bottom, there's no horizontal asymptote. But if the top degree is exactly 1 higher than the bottom degree, then that's the only time you get an oblique asymptote. So if this was like 2x to the third and then an x to the first in the bottom, the 3 is bigger than the 1, but it's 2 bigger than it, so then there would be neither a horizontal or an oblique asymptote. But if the top degree was 2 and the bottom degree was 1, then we would also get an oblique one. The one on the test, though, you just have to worry about vertical and horizontal asymptotes. Okay, next we have 43b. Solving an equation with an exponential equation. We've got a base of 5 and a base of 25. Try to make the bigger base look like the smaller one if you can. Sometimes you have to make them both smaller. But here we can make 25 look like 5 squared. 25 is 5 squared. So we can replace it with that. And then we can take the 5 squared raised to the x minus 3 and multiply those exponents together. So that becomes 2x minus 6 if you distribute the 2. Once the bases are the same, then you can cross them out. And then you're just solving a basic algebra problem. 3x plus 6 equals 2x minus 6. Subtract 2x from each side. X plus 6 equals negative 6. Minus 6 from each side, x equals negative 12. So the whole key is, can you get the bases to be the same? Sometimes you can, sometimes you can't. 46b, that was an exponential equation. Here's a log equation. Log base 4 of x equals 3 halves. 3 parts to a log. There's the base, which is a subscript, log base 4. And then I like to say a log is an exponent. is equals, a log is an exponent, so 3/2 is the exponent. So if we transform this log equation to its equivalent exponential version, say to yourself, which of these three things is a base? The 4 is. Which one's an exponent? The 3/2. So we can write that 4 raised to the 3/2 power. And it equals the one part I haven't used yet, the x. And so x is already by itself. All we have to do is evaluate 4 to the 3/2. 3/2 is a fractional exponent, and that turns it into a radical. The 3 is still an exponent, but the divided by 2, that turns it into a square root. And you can do it either way, but I like to do the root first to make the answer smaller. The square root of 4 is 2, and then do 2 to the 3rd power and get 8. You could do 4 to the 3rd first and get 64, and then the square root of 64 is still 8, so it works either way. I just like to work with smaller numbers. That was 46b. 48a is where they give you 3 separate logs subtracted out, and they want you to condense it down to a single log. Write it as a single log. Here's kind of the slower way of doing it again. If you take them 2 at a time, subtracting 2 logs is the same as having 1 log divided. So the p and the q can be divided into a single log with base b. Then you do it again. I have 2 logs subtracted, so I want to have 1 log divided. Another way of thinking about it is any log that's positive, like the front one, in the final answer that p is going to be in the numerator. The 2 logs that are subtracted, they go in the denominator, then the q and the r go in the denominator because they're both subtracted. The pluses go on the top, the subtractions go in the denominator. And the answer is log base b of p over qr. It's just 1 log, a single log. 52c is like that 5 and 25 problem. But unlike that problem where we could turn 25 into a 5, there's no way to turn 5 into a 2. 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. There's no power of 2 that equals 5. So sometimes you're unable to make the bases look alike. Or actually, I'm looking at the wrong problem. We're supposed to be doing 52c. But same deal here. One base is an e, and the other base will turn into 4 eventually. If you first divide by 2 just to get that 2 out of there, e to the 5x plus 2 equals 4. There's no way to make 4 look like an e, obviously, just like we couldn't make that 5 look like a 2. So when you can't make the bases the same so you can cross them out, this is where you put a log on both sides of the equation. If the bases are both regular numbers like that 2 and 5 problem, then use common log, base 10. If there's an e involved like this problem, use ln, natural log. Put an ln on both sides of the equation. Because an ln cancels an e. ln and e cancel the same way square roots and squares cancel each other out. So the ln and the e cancel, leaving just the 5x plus 2. And then you got equal to ln 4. Now you're just going to minus 2 and divide both sides by 5. Now ln of 4 can be typed into a calculator to get a decimal version of it. So I would hit ln 4 and press enter, then minus 2, and then divide by 5. But notice the minus 2 is not getting subtracted from the 4. Don't try to do 4 minus 2. You wouldn't get ln of 2. You have to have ln of 4, get that as a decimal, then minus 2, then divide by 5, and it comes out to negative 0.1227. Okay, 53b. Here's another one of these problems with multiple logs. This time they're added together, and it's a part of an equation too. So just like those subtracting logs got condensed down to a single log, you can take 2 logs that are added together and condense them down to a single log. 2 logs added can be 1 log multiplied. Just like 2 logs subtracted made 1 log divided. So we got log base 5 of these two things multiplied together equals 1. Now there's only one log, so don't try canceling logs out. Here's where you want to transform to the exponential version. Which of these three parts is a base? It's log base 5, so the 5 is the base. A log is an exponent, the 1 is the exponent, so literally 5 to the 1. And then I went ahead and FOILed this out. If you FOIL this out, you'll get 3x squared minus x minus 2. So that's what 5 to the first would equal. Because it's got a square in it, we want to get it equal to 0 and try to solve it with a quadratic technique. Again, the one on the test comes out nicer than this and it'll factor real nicely. But here, unfortunately, it doesn't factor. We got to use quadratic formula again. So there's a bunch of these on the review that the school made here. But opposite of b, 1 plus and minus the square root, b squared minus 4ac all over 2a. The negative 4 and the negative 7, that'll turn into a positive eventually. Negative 1 squared is 1. And 4 times 3 times 7 is 84. So 84 plus 1 makes the inside of the radical 85. Clearly the bottom 2 times 3 is 6. And then you could just use a calculator and get square root of 85 in a calculator. 1 plus that divided by 6 is 1.7033. If you try to do 1 minus the square root of 85 over 6, it'll be a negative answer. And it'll be negative to the point of putting it back in the original problem would cause this domain to be negative. So that answer gets ignored actually, and there's only one answer instead of two answers. Normally with quadratics you get two answers. 57a. Here's a system of two linear equations, two lines. Two lines can cross each other one time at the most. You can use either substitution or elimination, whichever one you like better. I took the two equations and I noticed that one of them had a negative 5y. So what if I could turn this positive 1y into a positive 5y? So I multiplied everything in the second equation by 5. 2 times 5 is 10. 1 times 5 is 5. And 5 times 5 is 25. I just rewrote the first equation right above it. And this is the elimination or the addition method because the 5y's cancel each other out. 4x plus 10x is 14x. The y's cancel. Negative 11 plus 25 is 14. Divide both sides by 14 and x equals 1. But these two lines are going to cross each other at one coordinate, so we need to know what's the point where they cross. X equals 1 is only half the answer. Plug the 1 back into one of the two original equations. I just picked the one with smaller numbers and all positives. 2 times 1 plus y equals 5. 2 times 1 plus y equals 5. 2 times 1 is 2. Subtract 2 from each side, and y equals 3. So these two lines would cross each other at the coordinate 1, 3. Okay, we got two problems left. 58 is really the same thing, except now it's 3 equations and 3 unknowns. Solve the system. It doesn't matter if you try to eliminate x, y, or z first. You pick the one that's easiest. To me, the y's are the easiest because we've already got one case where there's a positive 3y and a negative 3y. They're already opposites of each other. And I've got a negative 1y that I could turn into either 3 or negative 3 pretty easily. So the strategy on these 3x3s is you got to eliminate one variable twice. I'm choosing to eliminate y, because these first two equations have opposite y's right off the bat. If we add them together, x plus 2x is 3x. The y's cancel. 4z plus 2z is 6z. 14 plus 10 is 24. So I've got one equation that just has x and z in it, no y's. So the key next step is I use the first and second equation to eliminate y. I now need to do either the first and third or the second and third equation. I need to eliminate y again. Don't eliminate x or z next. It has to be y twice. Whatever one you do first, you have to do that same one a second time. So I noticed that the third equation had negative 1y. If I multiply it by 3, it'll be negative 3y, and then it'll be the opposite of the positive 3y. So multiply the third equation by 3. 3 times 3x is 9x. 3 times negative 1 is negative 3y. 3 times z is 3z, and 3 times 9 is 27. Now add it all the way back to the first equation. X plus 9x is 10x. The y's cancel again. 3z plus 3z plus 4z is 7z. And 27 plus 14 is 41. So by eliminating y 2 different times, I've now reached the point that problem 57 was starting at. Now we're back to what we normally have, 2 equations, 2 unknowns. So now we have to eliminate either x or z, whichever one we think is easier. To me, 3 and 10 is a little easier than 6 and 7. And there's nothing times 3 that equals 10, so I can't turn that into the opposite of 10 real easily. Whenever that happens, you want to multiply each one by the other one. Multiply the 3 by the 10, and multiply the 10 by the 3. And one of them needs to be negative 2, so I just picked the first one. I'm multiplying the whole first equation by negative 10 and the whole second equation by 3. So the top equation will be negative 30x, negative 60z, and negative 240. The second equation will be 30x plus 21z equals 123. Now the x's will cancel. Negative 60z plus 21z is negative 39z. The 100 numbers add up to negative 117. Divide by negative 39, and it came out to 3 exactly, so that's a good sign we didn't mess up. Now, if you try to plug the 3 back into one of the original equations, you're going to get stuck because you'll have 2 unknowns. So you have to come to one of these that you created. Really doesn't matter which one. Plug it in, and I just went over here. I guess I had my 3 here, and I just went to this equation that had, this is one I created too, 10x plus 7z equals 41. So you'll get 10x plus 21 equals 41. So over here, 10x plus 21 equals 41, minus 21 is 20. Divide by 10, x equals 2. So now we know z equals 3 and x equals 2. Still don't know what y is. So now go back to one of the original equations. I think I picked the first one. X plus 3y plus 4z equals 14. Stick the 2 in for x and stick the 3 in for z. 2 plus 3y plus 4 times 3 equals 14. 4 times 3 is 12, plus 2 is 14. Subtract 14, you get 0. 3y equals 0, so divide by 3, y still equals 0. And then we write a coordinate alphabetically, x, y, z. X was 2, y was 0, z was 3. It's just a 3-way coordinate, 2, 0, 3. And the last problem is 61a. Similar to 2 problems ago, 2 equations, 2 unknowns, except now we don't get all lines. Now we have a line and a parabola. There's a parabola there because of the x squared. Now you can solve this with substitution or elimination. To me, the elimination seems to work well here because the y's are already opposite. And if I add these 2 equations together, the y's will cancel out. But x squared plus x doesn't combine together, so you literally get x squared plus x. And then the y's cancel, and 2 plus 0 is 2. Because you have a quadratic, you want to get one side equal to 0. Now this is how all those other weird problems that had the quadratic formula on them, on the test you'll get problems like this that factor real nicely. So this factors into x plus 2 times x minus 1. So therefore there's two possible x answers, -2 and +1. So you have to take them one at a time, plug them back into one of the original equations. If I plug them into the second equation, because that's easier to work with than a square, stick a -2 in for that x, and then there'll be a minus y equals 0. -2 minus y equals 0. Add 2 to the other side. Divide by -1, and y equals -2. X was -2, y was -2. So that's your coordinate, -2, -2. That's where one place where the line crosses the parabola. Do the same thing with the 1 answer. Plug 1 into x. 1 minus y equals 0. Subtract 1. Divide by -1 and y equals 1. So x is 1 and y is 1. There's two answers here, -2, -2, and 1, 1. That's all you have to do. I went ahead and graphed this just to show you why there was two answers here. X squared plus y equals 2. If you minus the x squared over, you get a parabola that's upside down because of the negative, and it's plus shifted up 2. X minus y equals 0. If you add the y over, you're getting x equals y or y equals x. That's just a diagonal line at a 45-degree angle right through the origin. So if I take a parabola that's shifted up 2 and flipped upside down, and then draw this diagonal line right through the origin, 45-degree angle, yes, it's true that the line crosses the parabola twice. It crosses right here at -2, -2, and it crosses again at 1, 1. So that's why there are two answers to this problem. When you do two lines, like two problems ago, two lines can only cross each other once at the most. But once you start getting non-linear equations like parabolas, then answers can happen more than once actually. Okay, so you've seen everything that's on the review, or everything that's on the test actually. So you can do more of the review if you like, but if you just focus on this video, then you'll do fine on the final exam. Any questions, let me know.